My name is Greg Woods, and I'm a software engineer on the drivers team at Neo4j. And today I'm going to share with you one of the interesting features in 4.0, and that is reactive connections. So let's dive straight into it. So first, I'm going to explain how query execution works in the previous version of Neo4j 3.5. So what we typically do from a client's perspective is run a cipher statement against the server, and then immediately afterwards we want to consume the results from that query. So we send a request to the server to send back all the records, and the server obliges, it sends back these records until either the query has been exhausted on the server, until all the results have been returned, or until possibly there's some sort of connection issue which stops the server getting through to the client. And I want you to think about this analogy using a river. So imagine the server is somewhere upstream in the mountains, and your client is somewhere downstream of the river. And the river kind of has a relatively fixed capacity. So if there's a light amount of rain or rain at the source of our river, and it's within the capacity that the river can handle, then there's no problems, right? The water flows right through, and we don't have any issues. But what if the mountains have a higher amount of rainfall this month, and it's overwhelms the river? Well, then we end up in a flooded situation, right? Now, bring this back to data. This is now just to the client being overwhelmed by this flow from the server, and the client having to buffer records on the client side, and this typically happens when the processing of records on the client side is happening at a slower pace than the server is sending them, right? So they build up at the client door. So what can we do to address this problem? So we could give our client huge amounts of resources to handle this buffering. So we could try to speed it up by provisioning more memory or CPU resources, and also trying to optimize our code so that it runs as efficiently as possible. But this might not be possible. We might be depending on some downstream service which we don't control. So it could be depending on a bottleneck somewhere outside our system. And anyway, this isn't particularly ideal, right? We're provisioning the client for kind of the worst case situation to handle the largest expected stream of data and be prepared to buffer these records. So this is a slight exaggeration of what can happen. We have a little bit of protection on the TCP layer in our network layer, but this is an abstraction that runs at a different level, which is not aware of Neo4j records. So we can do a little bit better. And in 4.0, we've redesigned our bulk protocol, which is the binary protocol that's sending this data back and forwards from the server, to do some more elegant pulling of records. So we do the same thing as 3.5. We run a cipher statement against our database. But this time we can say we want to consume some of the records from the response, okay? So we can pull some, and this time we say a couple of records. And it works as before. Now, this time the server just sends back a couple of records, and the client now has the time to process those records in its own time. And then when it's ready, it can send another request for additional records, and so on and so forth until either we've consumed all the results again, or there's some network problem potentially, or this time we can now gracefully terminate a query in the stream by discarding the remaining records if we're not interested in them. And now bringing this back to the river analogy, if we want to kind of control the flow of the downstream parts of the river, typically we build a dam, right? And in this dam, we have this nice gate which allows us to let the water out, let the flow increase downstream if our downstream parts of the river can handle it. And or if the downstream parts are getting overwhelmed, then we can close the gate and protect our downstream system. And obviously bringing back to the data analogy again, this is like holding back those records until the client is able to process them. And the key thing here is that the client is the thing that controls how much flow it can take. So, if the client can handle the huge amounts of data that's been received by the server, it can open up this gate and let the data flow as fast as it can. And if the downstream parts of the system are getting overwhelmed, then we just start closing this off and even stopping it, allowing, if necessary, just to protect our downstream elements from getting overwhelmed. And this is now kind of much a nicer situation to deal with, and to hammer home what the real benefit of this. So I thought I'd share with you the results of a little sample application which uses this feature, right? So what I did is I wrote a simple application using our driver, and crucially in Neo4j we can switch off this gradual pulling of records. So I can run this sample app a couple of times with this thing enabled and this thing disabled. And this application is literally just pulling some random records from the database and adding in a little bit of delay to simulate maybe some third-party system being slow. And this graph shows the memory usage for this app. So in our JVM, we see the memory usage goes from say 250 megabytes up to almost 800 megabytes. And as you can see here, this is literally those records kind of landing at the client door, and you see these big spikes downwards there. Garbage collection results when the queries when the results have been consumed. And yes, now we switch this on and we run it again. The red line. This is now, you can see a vast improvement on the memory consumption. So we've gone from maxing out at nearly 800 or 750 megabytes down to a maximum of say 40. And crucially, you notice that this is not necessarily faster, but it's being able to do the work at with the same speed as the pulling all the records at the same time, but with much less resources. And that's kind of one of the key benefits of this new implementation. And the thing that makes this all work is reactive programming and reactive systems. And whilst I probably can't build a comprehensive understanding of reactive programming in a 30-minute talk, it's kind of enough time to get an intuition and understand the benefits. One of the benefits obviously being this efficient use of resources. But don't worry, if you want to dig more into this later, if you find it interesting and useful, then I'm going to provide some links at the end, which you can dive into if you're curious. And so what is reactive programming? Well, in a short sentence, it's programming with asynchronous streams of data. I guess most people are kind of relatively familiar with streams of data and then asynchronicity. And this is, rather than kind of just being something in your language that you might use from time to time, this becomes like the core thing in everything you do, everything you code. So how does this work? We've gone from now this kind of imperative style of programming where you have state of your application and you execute changes to that state, from now defining like a pipeline of data and using this declarative style rather than imperative to define and build your applications, describe your application's behavior. So let's look at this from more of a concrete point of view with an example. So here is our asynchronous stream of data. On this time ordered. On the left is the earliest point in time, and the right is sometime in the future. And crucially, these streams can be infinite in length, right? That does not necessarily mean that they're finite. And things can appear on this line, data items. This circle represents some data. It could be Boolean, it could be a string, or indeed it could be a Neo4j record, right? And we have many of these things that can appear on the stream, potentially infinitely in time. All right, so we have our kind of really basic construct. What can we do with this? What is the next step for processing stuff here? This is the only thing, or the main thing we have. What we do is we write code or functions that react to changes in this stream of data, and then those function together with the streams define or drive the application's behavior. So let's dig into this more. This is a function, say, that would filter out all the circles that are green or blue. Right? So what we get in the end is a result stream, and we just starting from left to right, copy the things over that are either green or blue, right? Fairly straightforward. And then obviously not copying over things that aren't. And this kind of style of diagram is quite common in this reactive world. So what I want to do is share with you this diagram from a particular implementation of reactive programming, which is the reactive core implementation of the Reactive Streams API. I'll talk a little bit more about Reactive Streams in a moment, so it makes a bit more sense in a short moment. But this is now obviously a function that is, instead of filtering, well, it's still filtering stuff out, but it's now filtering based on whether these elements are distinct or not. So, we see a green one, a yellow one for the first time, a blue one for the first time. We've already seen a green one, so that doesn't end up in our result stream, and so on. And just a side note here about this notation. So you see at the end of the line, after the last blue one, you've got this black line that represents this, or notifies that this stream is finite in length. So this stream no longer produces record after this, or results after this this black line. And these are kind of the core elements of the style of programming. So you have these functions, you have these streams, and you functions, and you build them up into building your processing logic to build this kind of asynchronous pipeline that builds up to produce the functionality that you're looking to make. And what I thought it'd be helpful to build an even more concrete understanding of this reactive programming is to look at an implementation. So I thought I'd dig into a little bit of a Java implementation called Reactive Streams. And Reactive Streams is an API that's made out of 4 interfaces, together with a specification of how these interfaces interact with each other. And this thing is called Technology Compatibility Kit, or TCK. Yeah, and here are the four interfaces. And already 4 is already quite a small number. It's fairly intuitive to see what these things are, right? So we've got a publisher, which is obviously producing stuff. We've got our subscriber, which is interested in consuming stuff. A subscription, which is representing the one-to-one life cycle between a publisher and a subscriber. And then a processor, a little bit more mysterious, but it represents a stage of processing data or doing something to it. And we'll look at these in more detail now. So first, let's look at subscriber and publisher and how they interact with each other. So the subscriber calls to the publisher to say, I'm interested in subscribe to you, and it passes itself as a reference to the publisher, so it can use that to call back with the results later. And then in turn, now the publisher calls back to the subscriber with onSubscribe method, creating this subscription object in the process, passing that back to the subscriber. And now this acts as the ticket or the mechanism by which the subscriber can communicate back to the publisher how much records it can handle. So similar to the analogy of the dam with the gate in it, right? This thing is the thing that allows you to open and close, or open and control the flow of data which the subscriber is receiving stuff. So subscription has a couple of methods on it. One of them is request with an integer parameter. So that allows the subscriber to say, I want X number of records, or 10 number of data items. And also the subscription has a cancel method, which allows the subscriber to tell the publisher that I'm no longer interested in receiving any of your results. And just to finalize what's available in this on the subscriber side. So obviously the subscriber needs some way of receiving stuff from the publisher. So it has methods on next, which is just the next item in the chain. And on error, if there's some error that the publisher encountered, and it needs to pass that down to the subscriber. And then on complete, if the publisher is a finite stream, a finite list that it has no more things to pass on. And then, okay, finally, let's look at this processor interface. And a processor is just something that implements both publisher and subscriber interfaces. So it both consumes something from a publisher and pushes it out to a new subscriber. And then that's in the step of it's doing something to the data. Doing something to the data that it's receiving. So it's like the filter function, the color filter function, or the distinct function from the Reactive Core documentation. And then crucially, this thing is also able to respect the control flow from the subscriber, and it's the final subscriber in this chain which is driving the flow of the whole chain, right? So the subscriber would send a request end to the processor, and in turn, the processor would send that back up to the chain to the initial publisher. And another way this is commonly you'll find if you dig into more details is called back pressure. So it's a way of feeding back to the higher level elements in this chain what the lower parts can reach. And finally, you can chain these things together as many as you want to build a really complex and chain that describes exactly the functionality that you want in your application. And crucially, each step in the chain respects this back pressure element. And the whole chain is driven by that final subscriber. That's really key. And okay, so that's kind of like the high level view of what reactive programming is, and an example using the Reactive Streams API. Let's pause here and mention that Neo4j 4.0 is reactive to the core. What I mean by this is that you can imagine a situation where you could simulate reactive behavior on the client side by essentially moving the buffering problem or the flooding problem up to the server. So the client can have this nice memory management benefits, but the server can still overwhelm it. The server can still be overwhelmed and drip feed them basically to the client. But this is not what Neo4j 4.0 does. It's the whole chain of things is reactive. So from the moment you send a query to the server is then internally generating those results from that query in a reactive fashion so that you get these nice memory management benefits through the whole stack of your application. And that's something that's quite important. Right, so now how can you guys get your hands on these features? We've got reactive drivers in 3 different languages at the moment. We have Java, which uses that Reactive Streams, has a hook into that Reactive Streams API you mentioned. And also, so anything that implements the Reactive Streams specification, you can plug into your Java driver. And we also have a link into the Reactive Extensions approach. So it's another similar to the Reactive Streams API. It's another way you can define and declare reactive behavior. It's has a slightly bit of different terminology, but if you understand the Reactive Streams specification, you can relatively easily get an understanding of the Reactive Extensions approach. So we have Java, we have JavaScript, again using Reactive Extensions, and .NET, which is also using Reactive Extensions. So let's have a look at some coding examples. So starting with JavaScript. And if you're not familiar at all with the driver API, we have this driver object, which is the thing that's managing lots of things in the background for you. So things like connections to the database, routing information, and lots of stuff that's abstracted away to make things easier. And on this driver object, you can create sessions, and these sessions act as containers for your transactions to run in. And what we do is, if you run multiple transactions in a single session, you get some consistency guarantees about what each transaction can see. So if you run a transaction in a session which changes some data, and then the next transaction in that same session is accessing that data, there's a guarantee about being able to see those changes. So sessions act as containers for transactions. And we have three kinds of sessions. We have simple sessions, which are simple imperative style sessions. We have asynchronous sessions that allow you to consume things asynchronously in a language idiomatic way. We have reactive sessions now with 4.0. So we create this reactive session, and then on the session we can do a couple of things. We can either start a read transaction or a write transaction. And then this information is used to direct the query. If you're running your Neo4j in a clustered context, we use this information to direct which node, the appropriate node that the query should be sent to. Right, so to this read transaction, we pass in a transaction function, and on that transaction function, we run this cipher statement, right? Match product, where the product ID is equal to something, in this case 0, and we return the title from that node. And the next we do this .records, which is returning an observable that exposes each record returned by the executing query. And observable is reactive extension language for publisher, essentially. And then this pipe construct allows us to build a chain of processes essentially together. So here we are mapping or extracting the part of the result that we're interested in, which is in this case only one thing, the title. And then we can do this materialize method, which is wrapping the emitted data into a generic kind of tuple of error and completed. And then to array, we're just collecting all the results to into a single element, which is also an observable. Okay, so that's JavaScript. What about .NET? So this is a method which is returning an iObservable, which is again the reactive extensions speak for publisher, and it's very similar to the JavaScript one, right? So we've got a driver object. We do a reactive session to create a new session. We do a read transaction. We pass in a function. We run the same query as before. We get the records back with the .records method, and we select the parts that we're interested in. And then the slight difference here is that we're using this on error resume next, which just says if you encounter an error when you're running this thing, then do this, which is in this case we're simply closing the session. Okay, that's .NET, and then finally the Java driver. So in this case we've got another method. This time we're returning a flux, and a flux is the Reactive core implementation of the Reactive Streams API. This gets a bit complicated of a publisher. So you can essentially replace the word flux with publisher, and again we're doing pretty much the same stuff as before. We're doing running the query, and then in the Reactive core API we've got this using when construct, which allows us to basically automatically create these sessions for us. So you can still read as, I want to create a new session, a reactive session, and in our session do the read transaction and pass in the transaction function, run the query against the database again, and now build a new publisher result from the records of that query. And then in this case also we're printing out the results to terminal. And then finally consuming and closing the session once we're finished executing. And it's worth noting here, if you're into the Spring ecosystem, if you're particularly in the Java space, we're interested in the Spring ecosystem, then there's a really cool library which is just be interested to use, and it hooks into this reactive stuff. And it's my colleagues on the Drivers team, Garrett and Michael, are working on creating this SDN RX library. So if you're used to Spring annotations and Spring data, you can basically get a lot of stuff bootstrapped for you for free. And with annotations, get some really nice behavior. And the first version of that has just been released, so if you want to check that out, would be good. There's lots of examples in the code. So I encourage you, if you want to look more in detail, pull down the source code for each of the drivers. They come with lots of examples. These examples are included, and additional ones. So it's worth pointing out. But it's kind of worth pulling the 4.0 drivers down anyway, because to get some of the benefits of this nice flow control, all you need to do is upgrade to the latest drivers, and that means simple and asynchronous sessions also implement this flow control mechanism. So it's quite straightforward to get, after you've migrated your app to the 4.0 code, it's quite straightforward to get some nice this flow control features. And that's kind of the only things I had to mention. And thanks very much for listening. As promised, here are the links that I would suggest you follow if you're interested in going into this in more detail. So the first one being a really nice and gentle introduction to reactive programming to start off with. There's a link for the Reactive Streams specification that I mentioned earlier, and the other reactive extensions implementation. And if you want to go up a little bit higher in abstraction, you can look at the Reactive Manifesto and see what kind of kicks this whole thing off. And also the drivers manual is a great resource for finding out how to use the drivers, with lots of information on configuration settings and how to use them. If you're migrating, if you're already using Neo4j 3.5 and the corresponding 1.7 drivers, there's a nice migration guide on how to upgrade to the latest drivers. Since 4.0, we're now syncing the release versions with the server. So for this cycle, we've jumped from 1.7 to 4.0. So reason for that. And then finally, there's the link for reactive extensions, which is worth looking at if you're in the Java ecosystem. Okay, so that's kind of all I had to share with you guys. Check out some of these questions. See if you have any questions. Yes, so there's a question about reactive drivers in Python. So the Python driver for 4.0 is coming out soon. I think the alpha has been released recently, and there's a beta release due on Thursday this week. I don't believe there's reactive included in that, but after the 4.0 driver has been released, then we're considering extra features for 4.0. So if that's some feature you find really useful in the Python world, then that will be coming shortly after the 4.0 release. And okay, there's another question. So in the case where the client sends a lot of data to the server, does the server use back pressure to regulate the client flow? So yes, there's also flow control on the server side as well. So this is also respected in and also controls the flow. So this is Java Spring. Oh, this is if this question, is this Java Spring or EE? If you're referring to the SDNRX library, that's just Java Spring.